So now that we've defined density and volume, volume and mass, let's go ahead and look at density. Density is the amount of matter per unit volume. So, what do I mean? Well, if I look at these two marbles, this one's made of wood. Let's try to pick them up. This one's made of wood, and this one's made of steel. Do they have the same volume? Obviously. They take up the same number of space. Do they have the same mass? No, one is heavier. One has more atoms in it than the other. Although they take up the same space, we call that being more dense. What I mean is, in the same amount of space, there are more atoms crammed into the same location. Think about two classrooms. One classroom has 100 students in it. The other has 2 in it. Both classrooms take up the same amount of space. One is crammed full, and one is kind of open. That's density. Are y'all with me? So, same volume, different amount of mass. Or they could have different volumes, different masses too, but you hopefully get the idea. The formula of density is about as complicated as the explanation that was just provided to you. Okay, so density equals mass divided by volume. That's it. You take the mass divided by the volume. There's a nice little triangle you can draw for yourselves to always know the formula for all 3 values. What I do is I write a D, I put a line in between it, or right next to it, and I put a V on the other side for density and volume. Then at the top of that vertical line, I draw a horizontal line to make like a T, and I put an M on top for mass. This little triangle that we just created is the formula for each value. If I want to know the formula for D, or density, I cover up what I'm looking for, and I look at it. Mass divided by volume. Very convenient. If I want to know volume, I cover up volume. What's the formula for volume? Mass divided by density. And if I want to know mass, I cover up mass. Density times volume is the formula for mass. Nice and convenient. Now, in the metric system, or SI, density, or the density unit, is grams per centimeter cubed. The mass divided by the volume. In the US, the unit is pounds per inches cubed. Pounds per inches cubed. Now, you'll notice that the metric system is using mass, but the US system is using weight. Shouldn't that be slugs per inches cubed? In the US imperial system, we're using a type of density we refer to as density weight. This density is always true as long as you're on Earth. When you leave Earth, the density kind of changes because it's based on weight, right? This is going to work everywhere. We call this density mass. This is density based on mass. This is density based on weight. So what that means is we use this one for the metric system. It gets a little bit more complicated when we're doing it in the US system. What you do is you look at that M and you grab a wrench, and you take that wrench and you turn it over so that it's upside down. So we could say the US system has the D and the V on bottom still. We draw this little symbol, and we put a W on top instead. And this would be the US system, where you use weight instead of mass. You're getting technically density weight here. So, to convert these, as you can imagine, it's going to be a little complicated to go from grams per centimeters cubed to pounds per inches cubed. You got to convert grams to pounds, and then you got to convert centimeters to inches. There's a whole bunch of conversion. You do all that dimensional analysis stuff. Let me just give you the conversion rate. To convert from US to SI, all you do is you multiply your U.S. density, so pounds per inches cubed, multiply it by 27.7. And then to convert your metric system back to the U.S. system, what do you think you do? Divide your SI density by 27.7. To be clear, when I say U.S. density, I probably should have just wrote this, but what I mean is I convert pounds, I multiply whatever my pounds per inches cubed is by 27.7, and I get grams per centimeters cubed. And I take SI, I divide my grams per centimeter cubed by 27.7, whatever that number is. If it was 15, I would say 15 grams per centimeters cubed divided by 27.7. And it would give it to me in pounds per inches cubed. Just a nice quick conversion rate to save you all that dimensional analysis work. And then the last thing I'd like you to do in this section is tape in these common densities. And you'll notice in the metric system, they were very, very sure to make sure that pure water has a density of exactly 1. Nice, even number. They were very intentional to make it very conveniently exactly 1. Y'all see that? And then the U.S. system, they give us a nice round number 2, 0.036. They're very intentional with that to make sure water is nice and simple, easy to remember. Right? 0.036. That's just an easy number to remember. It rolls right off the tongue. You'll see what I mean when I say I just prefer the metric system. Now, if something is more dense than water, meaning it's a bigger number than water, its density is bigger than water, it will sink. If it's more dense than water, less dense than water, it'll float. That's why apples float and concrete sinks. Now, notice in the U.S. system, the rule still applies. If it's a number bigger than the density of water, it will sink. Is 0.06 bigger than 0.03? Then it sinks. Too easy, too obvious?